To understand what a logarithm is, you must first understand what a power is. So we already talked about 8 squared is 64, 5 to the 0 is 1, and 25 to the 1/2 is equal to 5. It's like taking a square root. So b to the x is equal to y, where b is the base, x is the exponent, and y is the power. Any of the two variables could be given, and you could find the third. All right, these, at least most of these, we should be able to figure out what x is more or less just by thinking about it and applying what we know about exponents and powers. 3 to what power is equal to 27?
3.
3, because 3 times 3 times 3 is 27. So x would equal 3. Now on number 2, we could solve this using cube roots, but some of you might just know that what number to the third power is negative 8? Negative 2. All right, on number 3, they already have x alone, but what don't we like about 3/2 to the negative first?
Improper.
No, I don't mind the improper. I don't like the negative exponent. How do we change it to have a positive exponent? What do you think? We could. That's going to make it a little messy. So one thing we could do, if we're not sure, is give that negative exponent to both the numerator and the denominator. And how do we make negative exponents into positive exponents? Moving them. So if 3 to the negative first is negative in the top, we would move it to the bottom, and the 2 to the first is going to move to the top. So we flip it. X equals 2/3. Number 4, we've got 4 to some power equals 1. That power would have to be 0. Anything to the 0 power is equal to 1. On number 5, 2 to what power equals 4? The second power. So x would equal 2. On number 6, 2 to what power equals 8?
3.
The third power, so x equals 3. On 7, 2 to what power equals 6? It's not 1, because 2 to the first would just be 2. So there's no integer exponent that's going to make this work for us. Notice that 6 is in between 4 and 8. So that exponent would have to be somewhere in between what two numbers? 2 and 3. So it's going to be some decimal. It's not going to come out nice. That's why there's a note by it on your notes sheet that this is when logarithms are useful. Okay, so we're not actually going to go ahead and solve this one yet. We'll learn how to solve this type of problem during this chapter. At the very bottom, this is already filled in for you. If y equals b to the x, then log base b of y is equal to x. You need to be able to switch back and forth between exponential form and logarithmic form. So we're going to have to be able to go back and forth between these two. The more we practice it, the easier it should become. Okay, so on the first one, we are going to be writing this with a log. What is the base going to be? 10. Log base 10. Notice that I wrote the 10 a little bit smaller and a little bit lower. Okay, when we write the base of a log, it's kind of like writing an exponent, but opposite. Exponents go a little high. Bases on a log go a little low. Log base 10 of what number? So if we look back on the previous slide, or previous page, down at the bottom there, it told us kind of the order things needed to go in. So yes, so if we wanted to, we could write off to the side those two formulas they gave us. They said if, I'll write it a little bit differently, if bx is equal to y. So you've got some exponent on a base equal to your power, then log base b of y is equal to x. So this is how we change it. So we already put the base down. The base was 10. What number should go by our log? The 100. Notice that it's the y. The y is whatever the power was equal to. So log base 10 of 100 equals... We got to use one of the numbers here. What's the only number we haven't used? The 2. When we rewrite logarithms, the base is always the base from the problem. So whatever had an exponent is considered our base. The exponent gets split away from it. So the exponent's going to go on the other side of the equal sign. And whatever the power was equal to is what we are now taking a log of. So we just have to get used to this pattern. So we'll try it again. On 9, what is my base on number 9? 10 of what number? Yep, you can put it as a decimal. We're not changing any of these. Yep, 0.01 equals -2. We're not really changing or evaluating any of this. All we're doing is rearranging it to write it as a log. It's just writing it as a different form. On number 10, what's my base? 2 of what number? Equals 3. All right, I want somebody other than Dana to help me out with number 11. What's my base?
4.
Of what number?
1.
Equals?
0.
Thank you. All right, we need another new volunteer to help us out with 12. What's my base?
3.
3 of what number?
81.
Equals?
4.
Thank you. All right, the last one is all written in variables, but we're going to treat it the same way. What's my base? K of what? Equals S. Good. So we just have to get comfortable being able to rearrange these from logarithmic to exponential form and from exponential form to logarithmic form. Questions before we keep going? Okay. All right, in your notes it says you can also evaluate logs and find the missing pieces. So that's what we are going to attempt to do on these. We should not really need them yet, no. Okay, our calculators, most calculators, which we'll get to this in the notes in a minute, most calculators default to a base of 10. Okay, there are not a whole lot of calculators that you can put in your own base on. There are some, but many of them default to a base of 10. So we have to learn a change of base formula. We just haven't gotten there yet. But we don't need them on these ones. So now we're going to switch from logarithmic form back into exponential form. So I'm going to have what as my base? 2. Raised to what exponent? The x, and it's going to equal 16.
16.
2 to what power is equal to 16? 2 to the 4th power. 2 times 2 times 2 times 2 is 16, so x would have to be 4. All right, on 15, what's my base? 3, again, we set this equal to x, so x is our exponent, equals 81. 3 to what power would equal 81?
I'm saying it's the fifth. Fourth.
The fourth power is correct. 3 times 3 times 3 times 3 would equal 81. We getting a feel for how to switch these back and forth?
Not this one. The last one I was going.
This is just going backwards from before. We're just switching it around the other way. Okay, on 16, what's my base?
1.
No.
5. My bad.
5. My exponent is x, and it equals... What does x have to be? 0. It has to be raised to the 0 power if it's going to equal 1.
So what's the answer of the x? Like x equals?
Yep, we were trying to evaluate it, so we set it equal to x because we didn't know what it was. So we figured it out. It's 0. All right, on 17, what is my base?
4.
4. My exponent
X.
is x. It equals 16. So my exponent has to be 2. X equals 2. Questions, concerns? We ready to kick it up a notch?
Yes.
Great. Here we go. All right, we're going to start setting these up the same way, but then these ones are going to take a little bit more brain power to complete. What is our base? Exponent equals. Okay, so this is a little different because we don't know some power that we could raise 8 to for it to equal 16. So instead, I'm going to use my knowledge of the fact that 8 and 16 are both powers of what number? 2. So this would, 8 I could rewrite as 2 to the... We could rewrite 8 as 2 to the 3rd power. It's still being raised to the x after that. Is equal to 16. We could write it as 2 to what power?
4th power.
The 4th power. If we are raising a power to a power, like 3 raised to the x, power to a power, what do we do? Multiply. So this is 2 to the 3x is equal to 2 to the 4th. Now our bases are the same, and we're saying that these should be equal. So that means that my exponents on the 2's should also be equal. Does that make sense? If I'm saying these are equal, the bases are the same, then the exponents should be the same. So I can just take 3x and set it equal to 4. Questions about that step?
I mean, I'll have to do a couple of problems like that again to actually get that.
Okay, we're saying both sides are the same. That means their exponents should match if their bases match. What's our last step to solve for x here? Divide by 3, so x equals 4/3. If you prefer to write that as like 1 1/3, you could. I would just leave it as 4/3. We ready to try another like that? Okay. Next we've got log base 9 of 27. We'll still say it equals x. What's my base?
9.
Raised to the
X.
equals.
27.
Thank you, Cody. All right, again, there's no nice power that I can put here to raise 9 to equal 27. But I know 9 and 27 are both powers of what smaller number?
3.
3. So I can rewrite 9 as 3 to what power?
3rd.
Not the 3rd.
The 2nd.
The 2nd power, I'm going to go ahead and give it that x. Power to a power we would multiply. Equals 27 is written as 3 to what power? the third power. Questions, concerns about what we've done so far? Okay, so I'm going to take 2x and set it equal to what?
3.
3. Those exponents should be the same. My last step to solve would be divide. We divide by 2, x equals, not 2/3, 3/2. If you want to put 1 and 1/2, you can. Don't need to. Questions about those examples? All right, I don't really know why they threw 20 in on this slide, but it's actually easier than those other ones. What's my base?
10.
Exponent equals,
100.
what is my exponent? 10 to what power equals 100? The second power. So x would equal 2. 21 is the hardest one we've seen so far, but we'll start setting it up the same way. What's my base? My exponent equals 1/32. Okay. Now, again, not really a great exponent that we know of that's going to help us out here. So instead, I know that 64 and 32 are both powers of what smaller number? 2. So I'm going to rewrite 64 as 2 to the no. 8th power would be too big.
5th.
5th is too small. 8th is too big.
6th power.
6. 2 to the 6th power is 64. Okay, if you're not sure, you can just start finding your powers of 2. 2 to the 1st, 2 squared, cubed, to the 4th, to the 5th, to the 6th, 7th, we don't need to go to. Okay, just list out our powers of 2 if it helps us out. Now, we are still raising that to what other power? To the x, right? So I'm going to put the 6 with the x, power to a power we multiply, is equal to. Now, this part gets a little tricky. We want to raise 2 to some power that's going to turn it into a fraction. That means that that power is going to have to be?
Fraction.
No. What? Negative. If you're going to take a whole number, give it a power, and it comes out as a fraction, then it would have had to have been a negative exponent. What do you think the number is? Could use this list I made you if you need some help. What? The negative 5th power. Good. Okay, we got the negative because we knew it turned it into a fraction. Put it underneath a 1. 5th power because 2 to the 5th is 32. Now I can use all of this to make a simple equation that I can solve for x. What's my simple equation? 6x equals -5. If these two sides are equal, the bases are already the same. Their exponents have to be equal as well. What do I do to solve for x? Divide by 6x equals -5/6. I talked about this just a little bit earlier when we asked about the calculators. A common log is a log that uses a base of 10. You can write a common log without writing the base. So log base 10 of y, we usually will just write as log y. Log base 10 of 100, we would just write as log 100. This is similar to other assumptions we make. For example, if I just write an x, what do you assume the exponent is?
1.
A 1. If I just write a root symbol like that, what do you assume the index is?
Square root.
A square root, or index of 2. It's the same kind of thing with logs. If they don't write a base, you just know that the base is 10. So add that to your mental list of things that you just know based on how it's written. Your calculator has a log button. However, the calculator will only do logs with a base of 10. That's not all calculators. Like I said earlier, there are some calculators in which you can enter your own base. But like those blue ones that I usually pass out, or the gray and black ones, those ones will not be able to enter in your own base. You gotta be a little fancier. Lucky for us, these examples are all using a base of 10. It's not written, so our base is 10, which means we can type them into any old scientific calculator. So you just find your log button, press log, press 5, press equals, and it should give you some number. That's the number we want to 4 decimal places.
Yeah, 0.6989. And since it's to the 4th decimal, should we round that last one up, or
Yeah, what comes after that? 9?
or 7?
A 7. So yes, so if we're rounding to 4 decimal places, the 7 makes the 9 go up. The 9 is then going to make the 8 go up. Okay, so our answer to 4 decimal places would be 0.6990. Questions about 22? All right, on 23.
How do we use the approximate sum?
Would that make you happier?
Yes.
Okay.
Yes.
Well, anything to make Dana happy. Okay. What about the log of 12?
Okay, so for that one, I got 1.07 out of 1.
What's after that 1?
It was an 8.
An 8? Okay, so if we're taking it to 4 decimal places, the 8 is going to make the 1 a 2. So 1.0792. One point what? 2, 4, 3, 5. What comes after the 5? 3. So that 5 is going to 1.2435. Okay. So on this slide, they were all a base of 10, which means that we can just use our calculator, plug it in, and then take it to however many decimal places they ask us for. Questions? Okay. Often, logarithms are used in real-life situations or in formulas. So here is a chemistry problem. The pH of lemon juice is 2.3, while the pH of milk is 6.6. Find the concentration of hydrogen ions in each substance if the pH is equal to the negative log of the hydrogen ion concentration. Now these really are not so bad. We're going to plug in what we know and then solve using some of the same methods we were earlier. So let's do the lemon juice up at the top. What was the pH of the lemon juice? 2.3. So negative log. Since we don't know the hydrogen concentration, what could I put there?
10.
If I don't know something, x. Trying to solve for it. Doesn't have to be an x. It could be some other variable. Okay, based on the way that they wrote this formula, And how we wrote it up here, what is our base? Nope. Nope. Anytime we see a log and there's not a base
10.
written, we have to know that it's a base of 10. Okay, now before I switch this to exponential, I am going to divide both sides by a negative, or multiply both sides by a negative, however you want to think about it. So now I have log of x is equal to negative 2.3. Now we finally arrive to the conclusion that our base is 10. If I'm switching this to exponential form, what exponent goes on this 10? From here.
X.
No. What is it? The negative 2.3. If it's not the x, it's got to be the other thing there. Negative 2.3, and that equals x. So that's that same formula that we used from the very front page of our notes. We're just rearranging it the other way. Now, lucky for us, in our calculators, we should be able to evaluate 10 raised to the negative 2.3 power. So remember that caret button I've talked about before? It comes in handy for this as well. 10 caret negative 2.3, enter. Gabby?
I can't find that button on my calculator.
Yours does not have a caret, it has an X box. So I would look for that button. Yours has an X with a filled in box by it. If you can't find it, I'll help you find it in a minute.
There's a 10 with a box. Oh, that's a lot.
Anybody get?
I got it.
What'd you get, Dana?
1.00225.
Let's see. Okay. So we got x equals 0.0050. We'll just leave it there. That one will make it stay put. Okay, so that is our hydrogen ion concentration for the lemon juice. We still need to find the hydrogen ion concentration for the milk. So we have to do the same process, except this time we're using a pH of 6.6. So again, I'm going to divide both sides by a -1 so that the 6.6 is negative now instead of the log. Okay, then our base is, if I'm putting it in exponential, my base is 10. The exponent on the 10 should be -6.6, and that is equal to x, which is, so that's what I'm trying to find. So again, in our calculator, 10 caret so it should be,
I got 0.000.
yep, yes, all them zeros. 0.000. How many zeros do we have?
We had about a good 6 of them.
6 zeros, and then the 251.
Yeah.
Okay, so your calculators, some of you, it might have put it into scientific notation, meaning it would have had 2.51 times 10 to the -7th. Okay, which if you put that, that's also fine. I would accept scientific notation on something like that. Okay, so what this is showing us is the acidity of these, which is also something that pH measures. But the more acidic something is, the more hydrogen ions it will have. So it makes sense that the lemon juice has a higher concentration of hydrogen ions than the milk. Lemon juice is more acidic than milk. I think most of you would have already known that anyway.